Okay, now we see your screen. Yes. Let me introduce the next speaker. So our next speaker is Professor Bohdan Feshchenko from Institute of Mathematics in Ukraine. And the topic of his talk is normal forms of functions with degenerate critical points on surfaces whose stabilizers are homotopically non-trivial. Yes, please.
Thank you very much. And I will start with some definitions. We consider a smooth compact surface M, and phi p we can denote a line or a cycle. The group of different morphisms, denoted by Bm, acts on the space of smooth function of the values of p of valued smooth functions, either following rule. The function and a different morphisms H is mapped to the following composition. And for a smooth function, we denote by SF and OF with a stabilizer. The stabilizer of this function and the orbit and the orbit of this function f. The stabilizer is a subgroup of the group of different morphisms preserving the function. And the orbit is a subspace of the space of a smooth function of this type. And by SID and OF, we denote a connected component of stabilizer containing the identity map and a connected component of the orbit containing a function f. And we have considered the following class of smooth functions. A smooth function f belongs to this class. This class f if the following conditions are satisfied. So for each connected component v of the boundary, the restriction of f onto v either takes a constant value or is a Kafkain map. A set of critical points, sigma f, is a degenerate union of smooth manifolds, and it contains in the interior of M. And for each connected component C of sigma f and each critical point P, at C there exists a local card near P and a local card near the image, such that the local representation of f near this point P is either a homogeneous polynomial without multiple factors with a degree greater than 2, or is given by this formula for some constant depending on C. So a function f has no critical points at the boundary. A connected component of the set of critical points is either an isolated critical point or a critical cycle, and this number NC from here can be either odd or even. At this picture, you see the foliations near isolated critical points. From the left, we have degenerate local extreme, and from the right, the generalized saddle. And from this picture, we see the circular neighborhoods of critical cycles. N is even and N is odd. This class of functions is large. It contains the class of course both functions and the class of functions with isolated homogeneous singularities, as well as class of coarse functions. The homotopy properties of stabilizers and orbits for smooth functions from this class with the only isolated homogeneous singularities are known. And for any function from this class, the following results holds true. So for a function f, the stabilizer is either contractible or has a homotopy type of a cycle, and to be more precise, it is contractible if f has at least one saddle point or a degenerate isolated extreme, or the surface is non-oriented, and other eyes to S1. So the stabilizer is contractible for almost all functions from this class. And it is interesting to characterize the functions from this class whose stabilizer is homotopically equivalent to a cycle. So denote by F0 a subclass of the class F of smooth functions which satisfy 1, 2, and 3b and 3a prime. So the only isolated critical points of a function f are Morse. And due to this theorem, a stabilizer is homotopy equivalent for all functions from this class. The following theorem holds true. If we have a function from this class f0, then m is one of the following and four surfaces. a cylinder, a disk, a sphere, or torus. A function is always null homotopy if M is not two torus, and a function on a two torus can be either null homotopic or not null homotopic. F has any finite number of critical cycles if our surface is a cylinder to disk and a sphere, or if function f is not null homotopic on two torus. And if f is null homotopic of function on two torus, then f has at least two critical cycles. And if our surface is a cylinder or a torus, then f does not have isolated critical points. And if M is a two disk or a two sphere, then a function has one or two non-degenerate extremes. And if we have a null homotopic as one valued of function, then there exists a lift f tilde, which is a smooth function from our class f0. And therefore, and so we will always regard null homotopic cycle valued functions and as real valued one. And to state our main result, we need one definition. The definition of a primitive functions from this class f0. These four functions are called primitive. The first three of them are height function, and the last one is a projection. And our main result is the following theorem. For any smooth function from this class for the surface, a cylinder, a two disk, or sphere, or f is not a null homotopic function on a torus, there exists a factorization where f0 is a prime function from this class, h is a diffeomorphism, and kappa is a function with which satisfies the following conditions. F has the only finite number of critical points in which it is not flat, and kappa does not have extremes at these sets. And this factorization is not unique and depends on the diffeomorphism H. And we will call it a normal form of this function.
I'm sorry for interrupting you. Just to say, you have 5 minutes left. I'm sorry. Yes.
Thank you very much. This is all.
Then I would like to thank the speaker for a very interesting talk.